Greetings, this is Chemistry with Nav. In this video we're going to take a look at the A2 section of carboxylic acids. So a carboxylic acid is an R group with a C double bond O and then a COH group attached. So we tend to write it like that, RCOOH, and the most common carboxylic acid that we tend to come across in chemistry is ethanoic acid, which is also has an old-fashioned name called acetic acid, which is vinegar. So we've got a couple of examples here which I want to go through and name. The first one is going to be methanoic acid, and that's based on the fact that there is only one carbon present, and therefore the name is going to start with meth. There are no double bonds, so the next two letters will be AN. If there was a double bond somehow in the structure, then those two letters would be EN. Obviously not going to happen if there's only one carbon. Looking at the second structure, we have three carbons. Now, in terms of naming priorities, the carboxylic acid group will always get the priority. So that will always be carbon 1. So in this case, that's going to be propanoic acid based on three carbons, but that hydroxy group is going to be sat at carbon 2. So we end up with 2-hydroxy propanoic acid. And this last one here is actually favoured in terms of analysis questions because it has a very odd molecular formula. But this is called ethane dioic acid. So whereas if there was only one carboxylic acid group, it would be ethanoic acid, there is an extra E in there for naming it, but also the di, showing that there are two carboxylic acid groups. And the molecular formula for this is going to be C2H2O4. And so the reason this is good for analysis questions is that the empirical formula, if we take the lowest whole number ratio, becomes CHO2, and that's the basis of trying to multiply it up and work out a structure from that empirical formula. So it's the fact that it has a very high number of oxygens compared to its carbons that causes some confusions for students when they're trying to work out the structure. Okay, so that's naming them. Let's look at a bit more about the structure here, and we can see that there's the possibility of hydrogen bonding on that molecule, and that's going to lead to solubility in water. And the reason for that is that the OH group is present here. So we have a delta minus delta plus dipole across that, but there's also the lone pairs on that oxygen. We also have lone pairs on the double bonded oxygen. We also have a dipole here as well of delta minus delta plus, which means that there is a lot of possibility for hydrogen bonding. You can have hydrogen bonding here going to an H. You could have hydrogen bonding here also going to an H. You can have hydrogen bonding here going to an O. So this molecule ends up being very soluble because it can make many hydrogen bonds with water. In terms of the chemistry of carboxylic acids, they tend to make salts, and these salts follow the standard sort of acid reactions where we can have a metal plus acid going to salt plus hydrogen. You can have a base plus the acid going to water and salt. Or you could have a carbonate and an acid going to water, CO2 and salt. So these are the things that you would expect from pretty much any acid. So carboxylic acids are good acids. That metal could be such as magnesium or sodium. We could have bases of alkalis that we know very well, so an aqueous solution of sodium hydroxide, or perhaps a solid such as magnesium oxide. And in the carbonates, we could use something like sodium carbonate, Na2CO3, which is a solid, which would still cause that reaction to occur. Remember that bases are metal oxides and metal hydroxides. Those are two of the important base groups that come up commonly in A-level chemistry. So these salts that are produced, let's look at the structure of those then. So we get something called carboxylate salts, because they will contain the carboxylate group, which is the RC double bond O and O minus, because the ethanoic acid or the carboxylic acid is an acid, so it's going to form H plus ions when in solution, which leaves that structure behind. So let's just look at the name of a couple of those. So if we had CH3, COO minus Na plus, that would be sodium ethanoate. And if we were to use something like magnesium in that structure, just be aware of how to write the salt. So because magnesium is 2+, we're going to need 2 of the ethanoate ions in order to balance that formula. But that name is magnesium ethanoate. So just be aware of that. The charges you can put in if you want to, but obviously with that doubling up of the ion in the bracket, it's easier to leave them out. And lastly today, looking at the reaction of carboxylic acids with SOCl2. This is for OCRA only. So if you take your carboxylic acid, here we have propanoic acid, which is CH3, CH2, COOH. We're going to be forming an acid or an acyl chloride. And acid chloride or acyl chloride is the same thing, two different names given to the same substance. React that with your SOCl2 and we effectively replace the OH group on the carboxylic acid with a chlorine. So here we have something called propanil, OYL, chloride, as well as making sulfur dioxide and HCl on the side. And the structure of that is going to be 3 carbons long, CH3, CH2, C double bond O, Cl. So it's prop because there's 3 carbons. The anoyl tells you that it's C double bond O and the chloride with the Cl at the end. Remember, there's also going to be quite a lot of other reactions of carboxylic acids. Check with your own exam board specification as to what else you need to know.